So now that you have the decision tree, you can use that tree to sort of parse the three major types of categories, or the different types of tests of significance that you do. You'll always do the Q-test, and then sometimes you'll do the F-test when you have two variables. Otherwise, you're either doing a paired t-test, a pooled, non-pooled, or a regular t-test. And I'm going to walk you through just an example. This comes out of your book, but I'm going to show you how to do it in Excel. I'm only going to show you how to do one of these, but it'll include an F-test and a T-test, and with the decision tree and this guidance, I think you'll be able to then figure out on your own how to do the other two tests. The confidence interval test is actually really easy to do, and you don't need Excel to do that. Okay, so what I grabbed is this figure, our table 4-3 that comes straight out of your textbook. This is coming from edition 7. And what it refers to is actual classical data. This comes from this guy, Lord Rayleigh, who won the Nobel Prize in the early 1900s. And what he was doing is he collected two sets of data here. These are his real data from his lab notebook. And these are masses of error, but they're computed two different ways, two different methods. And the first column says from air, and the other says from chemical decomposition. And in the early 1900s, most people knew, including Rayleigh, that the atmosphere, the air around us, at least when it was dry, was comprised of roughly 80% nitrogen. Most people knew that. And so what Rayleigh did was he wanted to know, if you zapped out that oxygen, and you just had the nitrogen, or whatever that nitrogen was, if you just had that and you weighed it, could you get density and then use that to determine what it exactly is? And does it matter the method by which you do that, the experimental method? And so first method, which he says from air, is he just took air and he actually just ran it over top of a red-hot flame, a burning hot piece of copper. And what happened was, when you have really hot copper, it's super reactive, prone to oxidation, when in the presence of oxygen. So it reacted with all the oxygen in the air, which is roughly 20%, and left just the non-oxygen parts of air, which in this case was mostly agreed upon that it was probably going to be nitrogen. And so then he took that, collected it in a sealed round bottom, and weighed it. And that's what you're seeing is the mass of those round bottoms, or they had air. Then he generated nitrogen from a chemical decomposition. So instead of doing it from air, he got a pure sample of nitrogen by taking ammonium nitrite, which is NH4NO2, and he heated it up till it decomposed. He already knew that if you decompose that, it would generate pure nitrogen gas. And so he did that, and in the second column, he had pure nitrogen gas generated from the chemical decomposition, and he weighed that. And so in principle, the hypothesis was, well, if air truly is, once you pull out the oxygen, if it's truly just nitrogen, then those two sets of data should be identical, or their averages should be identical. Of course, they're not going to be exactly the same, right? Because we know random error will never allow them to be the same, but are they statistically the same? Meaning they come from the same population of data, even though they're two different samples. That's a question for statistics. And so if we were to go through our decision tree, we'd start at the top, of course. We'd pull out extraneous values using the Q and grubs. Rayleigh did that, and so the data sets we have now are cleaned up, and we have these three possible cases. One is compared to a known value. We're not doing that. We don't have a known value. We have two sets of data, and so it's one of these two sets. Are we comparing two sets of measurements, or are we comparing two methods on a single set of samples? That feels like semantics, but it's really important that you understand the difference. In this case, think about what Rayleigh was doing. He was, in one case, measuring the air itself and then removing oxygen and weighing it. And then in a totally different set of measurements, he was taking a solid compound of ammonium nitrate and heating it up and generating nitrogen gas. Those are two different sets of samples and two different sets of measurements. They are not the same set of samples measured by two different measurements. So that rules out our paired t-test and puts us in the center here, and which is why I chose it, because it's a little bit more complicated, right? So now we're comparing two sets of measurements. the error and the chemically decomposed error, and now we need to deduce whether or not the standard deviations are different, so we have to run an f-test. So we could do this by hand or in Excel, and I'll show you two different ways to do that. So of course the sort of brute force way would just be to compute the average and standard deviation. So I'm just going to type in average here, and then I'm going to set a formula equal average, and then I will put a parenthesis, and then I'll drag down for my values from the error. I'll close the parenthesis. I'm going to copy that value and paste it here. It's going to default and copy my formula over. I can double click that just to ensure. You can see it didn't grab that last value, so I'm going to pull that down, then press enter. Now I've got the two averages. I'll bold that. Now I'm going to compute the standard deviation, which is S in this case, because it's for the sample. So that's equals STDEV, parentheses, and then drag over that first data set, and then I'll do the same thing here, copy and paste it, and I'm going to grab that data. So if you look at my two standard deviations, and they're slightly different, and my means are slightly different. And again, the question that we're trying to answer is whether they're statistically significant in their difference. Are they truly coming from different populations, or is their difference not simply able to be described by random error? Okay, so remember that the f-test is the first standard deviation, S1 squared, divided by S2 squared. The square of the standard deviation is also known as the variance. Doesn't really matter if you know that, but I'm just going to type that here, and I'm just going to compute it. So equals that thing, and then caret symbol to the second power. I'll grab that, and then I'm going to copy and paste that formula. So now I have my S1 squared and S2 squared. So that'll allow me to compute my F value, or F statistic, the calculated version of that. Remember, that's just going to be S1 squared over S2 squared. So that is my F calc, which is 0.01069, and I need to compare that to the tabulated version of that. Before we do that, remember, we're going to need to know the degrees of freedom of each of my data sets, which is going to be the number of measurements minus 1. So how many measurements do I have for air? I have 1, 2, 3, 4, 5, 6, 7 measurements. Minus 1 is 6. And for my second standard deviation, I have 1 extra, which means I have 1 more degree of freedom. I can pull up my table, and in this case, remember, my degrees of freedom for S1 were 6, which would put me here. Let me double check that. 6 and 7. So 7 over here, which means I need to move over on my table. That's 3.87. That's my table value for the F statistic. So I will just type F table here, and I'll put 3.87, and then remember the criteria for determining statistical significance is, if we go back to our table here, if the calculated F value is greater than the table value, then those standard deviations are statistically different or statistically significant. They're different. Our F calculated value is much less than our tabulated value, so we can say that these S values come from the same population with 95% confidence, because we used a 95% confidence table. That's the first way that we can do it in f-test. The second way uses the data analysis package in Excel, which is also what you're going to use to do the t-test. So let me show you that. So if you took Chem 108 with me, then you've used this before. If you haven't, you'll go up to Data, and then all the way over on the right, there's this button called Data Analysis. If you don't have the Data Analysis tool pack installed, you'll have to go to File, and then you'll have to go to Options, and then under Options, there will be an Add-ins button all the way to the left. You'll click Add-ins, and then you'll find the Analysis tool pack from the active application add-ins or the inactive, either way, and you'll click it, and then you'll click Go, and then you'll make sure that the button is selected to include the Analysis tool pack. So right now you can see mine is included. If yours is not, select it, click OK, you may have to restart the program, so save your data and restart it, or not. But then that will give rise to the data analysis pack on a PC. If you have a Mac, there's slightly different instructions, so just give data analysis tool pack Mac a quick Google and you'll see a YouTube video to walk you through that. So we'll click data analysis, and then now you've got a whole bunch of new statistical operations that you didn't have available to you in just a standard Excel package. You can do ANOVAs, you can do correlations, covariances, etc. Here's our F-test. Our t-tests are down below. I'm going to select the F-test, click OK, and it's going to bring up this new window that says F-test to sample for variances. So it's asking me for my variable 1 range and my variable 2 range. So those are my two data sets. So my variable 1 range, I'm going to click that button and I'm going to select my data. So just the data from my air sample. And I'm going to do the same for variable 2, but this time selecting from my chemical data set, select that whole thing. The alpha value here is essentially 1 minus the confidence interval. So if you want 95% confidence interval, then your alpha would be 0.05. So the default here for the F-test is just fine. Then for output range, I'm going to select just a cell on my spreadsheet and then click OK. And that's going to generate my F-test results that look like this. And so you can see that it automatically computed my mean values, which is the same as my average values over here. It computed my variance values, which I computed here as the square of my standard deviations. Here are the number of measurements I did, and then -1 to give me DF, or my degrees of freedom. My computed F statistic here is 0.01069. Which is there, and then my F critical 1 tail is here. You can see that actually my my F here, this is my calculated, and then F critical, this is my table. My table value is slightly different here for this Excel computed value. And that's actually probably a better approximation of reality, and the reason is because this is assuming only one tail as critical in the normal distribution rather than considering both tails. And so this is actually a sort of more stringent criteria. Either will be acceptable in this class as long as you walk me through what you did. So again, we'll compare the F-calc to the F-table. If F-calc exceeds F-table in value, then it's statistically significant in difference. So in this case, F-calc is considerably less than F-table, and so we'll draw the same conclusion that these values are coming from the same population, and we know that with 95% confidence. Okay, so that puts us back at our decision tree. We just ran our F-test, and we determined that the standard deviations of these two samples are not significant in their difference, meaning they come from the same population mean and standard deviation. They come from the same population in general. So that means we need to do a 2-sample t-test with pooled standard deviations. So we could plug all this into an Excel spreadsheet, but I'm not going to do that because it's going to take us forever to do that, and we're very likely to make a transcription error. So I'm going to do this. So back in Excel, we're going to go back up to data and access the data analysis tool pack all the way over here to the right. I'm going to click that. I'm going to scroll down to my t-tests. I have 3 t-tests. Coincidentally, those correlate with the 3 different t-tests in the decision tree that I mentioned. So you have t-test paired. So we have the paired t-test, which would be the one all the way to the right in the decision tree. We have the 2-sample assuming equal variances. When we assume equal variances, that's the same as saying that the standard deviations are not statistically different, meaning we're going to do a pooled standard deviation t-test. And then we have a t-test with 2-sample assuming unequal variances, meaning an unpooled t-test. So we had decided or figured out from our F-tests that the S values come from the same population, so we can pool or assume equal variance. So I'm going to select OK. It's going to prompt me with a window that's very similar to my F-test where I have variable 1 range and variable 2 range. I'm going to go in and select those, variable 1 being my air data, variable 2 being my chemical data, And then again, alpha is going to be 1 minus my confidence interval. And in chemistry, analytical chemistry, you can just assume 95% confidence for everything we do in this class. There's no reason that we're going to deviate from that, at least within this class. And so the default in Excel will always be 0.05, and that's always going to be good for you. You can leave hypothesized mean difference as blank. We don't need to do anything there. Again, I'm going to select output range. I'm going to select this button, and I'm going to just click here just below my f-test, and then I'll click OK. And now that's going to generate this new table down here. And what are the key values? Again, it ran a mean and a variance observations here. It pooled my variance together, which is what you would do if you were doing this by hand. So that's the sort of computed standard deviation for the whole set of data, assuming it's all coming from the population. So you essentially take the standard deviation of everything. My degrees of freedom for the whole set of data, which is 13 now because we're combining the two. And now we have our t-stat, which is the calculated. T-stat is the same as t-calc. I'm just going to write t-calc here because that's what I have in my decision tree. So there's t-calc. And then we have a few different options here. We have t-critical 1 tail and t-critical 2 tail. And in this case, we're going to consider only the t-critical 2 tail. And so we're thinking about both sides of the normal distribution. Does our mean value lie out in the tail, either to the far left or to the far right of our normal distribution? If you have reason to believe that you have some systematic error where it's causing your mean value to be on one side of the distribution, then it might be useful to do a one-tailed t-test, but that's beyond the scope of this class. We're only going to do the 2-tail. We're going to compare these two values, and again, as all the points of criteria for determining significance in terms of these statistical tests, we're going to take the calculated value and compare it to the table value. If calculated value is greater than the table value, then they are statistically different. We can see the calculated value is 20.2. The tabulated value is 2.1. That means that the statistical difference between these two data sets is significant. And we can go so far as actually looking at this next variable here, which says p. This p 2-tail, is actually the probability of finding these two means in the same population. And the probability you can see is 3.3 times 10 to the minus 11, which means that these are really different from each other statistically. There's almost zero chance that the difference in these two data sets can be explained simply by random error. That's what this tells us. That probability is so tiny. So, moral of the story, this was the real data set that won Rayleigh a Nobel Prize. And you can see that these numbers are really, really similar to each other. And if he were not careful in his measurements, not just not being careful in his measurements, but if he was also not careful in his analysis and just said, yeah, these numbers are pretty close, they're close enough, that must be the same thing, which a lot of us would do, to be fair. If he were to have done that, he would not have made this big discovery. So what he found out was that these are statistically different and that error is statistically just a smidge heavier right here. So the average is just a smidge heavier. What did that come from? Well, that comes from argon, the noble gas in air, which Rayleigh discovered by this set of data. And so it was really important. That tiny, tiny little percentage of argon in our air, that noble gas, which are really hard to detect because they don't react with anything, he figured it out simply by a small statistical deviation in averages and using a t-test like this.